පුතලා ඇහෙනවද? මේ ගන්නපුටේ මේ රෙකෝඩින් එක රෙකෝඩ් වෙන වෙලාවට මේ රෙකෝඩ් එකට ඉන්ටරප්ට් කරගන්නත් බෑ. බලන්න මේ ඇහෙනවද කියලා. Yes, yes, I'm talking now. ඇහෙනවද? පුතා ඇහෙනවද? ඇහෙනවනේ. ඊයන්සේ මේ ගන්නපු රෙකෝඩ් එකත් රෙකෝඩ් වෙනවා. හොඳයි. මේ තව කට්ටියගේ confidence එක build up කරන්න මම මේ ගත්තේ this slide is from NASA website. See here, this is about enthalpy. Enthalpy. And please note enthalpy, the blue color, what you see here. Yeah. Blue color, enthalpy is equal to capital H, is equal to capital E plus pressure times capital V. Okay. Here enthalpy capital H means this is not for 1 kg. For any mass, this is capital H. Here, capital E means this is not for 1 kg, this is for the mass they are considering. That's why for internal energy here, yeah, we have used U, but here in this website, for internal energy, they are using E. See, under the enthalpy, see the letters. E means internal energy. T means temperature. Simple P means pressure, because pressure is, no matter the size of the mass, pressure is pressure. There is no change. We call this intensive properties, because it's nothing to do with the size of the mass. It's in your notes. Okay, you have to go through the notes. V is volume, not specific. Big V. Q is heat transfer, W is work, Cp is heat capacity. Yeah, if you have anything unknown, don't worry, we will know everything. So here, define a new state variable that is a combination of other state variables. So enthalpy is a new variable, it's a definition from the other variables E plus PV. State variables means the condition there at that time, the air or gas or maybe two-phase. At that time, the temperature, pressure, and all the things we call we call it state variables. State variable. So here you can see H is E plus PV. It's the same like H is U plus PV. Okay. H is U plus PV. It's the same like that. So H is E plus PV. Okay. So for 1 kg, see specific enthalpy. Enthalpy divided by the mass. Mass means how many kilograms of the system. How many kilograms. So small h, specific, E by M, small e. P times small v. Okay. So let me do this way to share with you. H equals U plus PV, and there I will check capital H is M times small h becomes kilojoule. So capital H is M times small h means what is small h? U plus PV. Okay, U plus PV. M times U plus PV. Now unit is kilojoule. So if I expand this, this is equal to M times U plus M times P times V. Okay, so that is equal to, I'm explaining this but not. So lifetime one time learning, yeah? Yeah. So don't worry, yeah, try to understand to the fullest. So I get this M here, rearrange this. So M times U means okay, Bhutala, some areas no power cuts it seems, but try your best to remain if possible. M times U is big view and M times V. Okay, I keep it here also, I will keep M times V. Okay. That is M times U is big U plus P. M times V is the volume of that mass M. So this is V. H equals U plus P. Or you can say it as U means E plus P. H equals E plus PV. Okay, that's why the NASA website you can see H as E plus PV. Quite interesting. Okay. That's why in the NASA website, you notice this because H is U plus P or E plus P from the previous. for given mass H equals U plus P. H equals U plus P. So if you work reverse, same like this, enthalpy divided by mass is U by M plus PV by M, or E by M plus PV by M, all divided by M, all the terms. Then what happens is H by M becomes small h, U by M becomes specific small u, V by M becomes small v. So E by M becomes small e, P times V by M becomes small v. So you can see H equals small e plus PV amperes. That is specific enthalpy. Okay. I believe you have some good idea. Yeah. So here, so below the enthalpy definition, the rest uh, we will come back, okay, and we will go to the next session, next slide. Okay. So enthalpy is H is E plus PV, that is from NASA website. For 1 kg, you can see this is H is U plus PV, or E plus PV. Okay. For mkg, V is M times V, U is M times U or M times E. H is M times H for mkg. So this becomes H is U plus P V of M, Vp, and that is H. Yeah. There's a mass, here maybe molecules, any gas or liquid, whatever. For the given mass, you have the boundary here. Within the boundary, the mass of our interest, we call this system. Because so many molecules, we call this system. And this black line is the system boundary. Okay, black line, inner side is the system boundary. And outside the boundary is surrounding. Okay. Outside of the boundary is the surrounding. So this is surrounding. This is surrounding. Surroundings. Outside the boundaries. Okay. So everything is surrounding. I leave it like this. White color is the surrounding. So the system is here. This is your system. Message. Oh, cannot hear. How to say? see whether now you can hear or not. This is a computer mic anyway. So this is the system. I just tilt the computer, see whether it's okay or not. The system is the surrounding. System. Okay. System, surrounding, and the boundaries here. System boundary. System boundaries here. Oh. Cannot hear anything. Puta, can anyone hear? If yes, if can hear, say yes. Hello, can anyone hear? Puta, lahinada? If anyone can say yes here. Hello? Hello? Lamaya hinada? Puta lahinada? Hello?
Yes, sir.
Okay, good.
Yes, sir.
Good. Okay, Puta. So here is the system boundary. This is the boundary. System boundary. Okay. So you can see internal energy U. Okay. And internal energy U. Pressure P. See big V for the volume. Okay. So P times big V and U have the same units. Okay, you have to notice this. P times V and U have the same units. And this is energy unit. Okay, energy unit means joules and kilojoules. Energy unit, joule and kilojoules. Interesting. So what is this PV? U, we have some understanding. Why? U connected with PV and define a term U plus PV as enthalpy. Why is that? Those questions we need to get answers for that. Okay. Same like entropy, we have some understanding. It's about the reflection of unavailability of very useful thermal energy. That is what we are losing anyway. Losing of useful thermal energy. So here for energy, So P times V, and you have the same units. So why we have U plus PV? There are reasons, okay? Very valuable reasons, because NASA, they mention enthalpy because in the rockets and all, you can see the working fluid. You know the word working fluid because we have shared that knowledge. Working fluid passing through the rocket, the nozzles and all. So that kind of the open systems. The rocket has open means the mass can pass through the rocket. Okay. So open systems, the H is the matter most, because in propulsion, the high pressure, okay, later exposed to atmosphere become very low pressure. So huge pressure drops. And that is because of that pressure differences, this high pressure gas expands and then moves out behind the jet or the rocket. So the machine or equipment or a satellite can move forward. So we call this, anyway, we call this propulsion theories. In the propulsion theories, we use enthalpy. Even in aircrafts, you have the big turbines, you have a stream of, okay, stream of hot gas finally leaving the nozzle behind the turbine. And as a result, the aircraft moves forward. So that kind of open systems, turbine is an open system. Yeah. Open means, let's say example, when you cook rice, you put rice on the cooker or pot and you close the lid. If you close the lid, assume no moisture can go in, no air can go in, nothing can go out. It is closed. But in aircrafts and all, open systems. Open systems, this H is the matter the most in the calculation. Okay? Even in compressors, engines and all, we will be using H. Let's say. Now, we move forward. So, U and T, we have the same values, and why we need U plus PV. So this is the slide. U and P here. We have some gas here. So let's say this system seems like a rocket, let's say. So comes in, when some comes in, some should goes out. Okay, some should goes out. So somehow, because of this moving of this matter or mass into this volume V, you have to replace some volume V inside. We have to let some internal volume of mass V go out when we need to move in another equivalent mass with the volume. That's why to displace this must have extra energy. Okay, extra energy. We call this flow energy. So the work done by force, okay, due to P, because of the pressure P inside, we have to done some work on this gas moving inside. We have to push this to the system. We have to push this. So this is something like, because of that, this needs some extra PV. Okay, PV is necessary here other than U. Only U cannot come in. There should be some pressure, force. We call this P times V somehow. Okay, if we need to fill this U plus PV. Okay, so this U and P. Finally, of course, you have to have U plus PV. This is difficult to understand. Let's say this way. Initially, this is a piston cylinder. You have internal energy U, pressure P, volume V1 and force F. Now what happens is this piston moves a distance D, let's say. So the work is force times D, Fd. Force is pressure times area. So work is pressure times area times D. So area times D means displacement. So this mass displaced by D. Piston also moves. Mass also displays. It expands. Mass really expands. Okay? And it is something like when mass expands, it is something like displacement. So the displacement is what? V2 minus V1. See, W is work done here is pressure times V2 minus V1. Okay. If you have a constant pressure, let's say here we consider same P. So for this displacement of mass, you can say piston displays, of course, true. But the mass also expands. Yeah, expands. Yeah, here mass expands. So if you continue this to the next slide, next slide. So this is something like the work. So let me develop the next slide. Okay, next slide. Next slide, if you develop, so let's say here initial it is U1, okay, and here with the expansion again you have U, but let's say that is U2, okay, U2. So this one I will put as big U because that is for the same mass. Big U. Okay. Big. Yes. So force F is here. Same F, and then we can see the piston displacement. So here I take volume expands, V2 minus V. So now what happens is, this force F was, this energy for the force is from this gas or steam, this system, this F is there. And because of this energy, U1, okay, because of this energy U1, part of that converted to work, okay, part of that converted to work, and the remaining energy is there as U2, okay, part of that. So I'm going to write the equation here. I'm going to write the equation here. Okay. Yeah. Okay, this is important by moving a volume V. Okay, work done by pressure force. This one, W is Fg, that is force into force. Force is pressure times area. So W is pressure times area times D means area times G. So area is the piston area, piston area. And area times D is V2 minus V1. So that is redisplaced, I just mentioned here. So W is P times V2 minus V1. Redisplaced is P times V2 minus V1. Then I will look into the energy within the system. Initially this has U1. From that U1 some work is done. Okay? And there is a balance of energy U2 because from U1 work is done. Let's see. Okay? So this is the, so somehow this is internal. Okay? Within the system, this is how it is. So this case, I just mentioned to you, U1 minus W. Let's see what happens. Let's see what happens. Minus W is P2 minus P1. Minus W is P2 minus P1. Minus W is P2 minus P1. In a second. Okay. U1 minus W is U2. So U1 minus P, V2 minus P1 is U2. But let's say in an engine or in a rocket, to do this one, for this internal energy U1, there will be some addition of energy because of the combustion and all. Okay? Because of the combustion and all, there will be energy addition. Okay? Let's say this energy addition, because because of the combustion of the fuel in the combustion chamber. Let's say this energy addition is Q, okay, a big Q, okay, a big Q. Somehow this is addition because of the combustion, okay. So I will add this big Q here, the heat due to combustion. Yes. This way is okay, heat due to combustion. So now for this system, we have Q as well. Initially, before combustion, we have U1 and also we have this Q. So Q plus U1 is the energy here before expansion. So expansion means somehow a work is done minus W. That is U2. So Q plus U1 minus PV2 minus V1 is U2. Okay, is U2. So I need to take some space here. So I will duplicate this. I will duplicate the slide. And let's say I need to get more space here. From this, see, I move this part all to the other side. This is Q. And here you can rearrange minus minus plus. Okay, so this is U2 minus U1 plus PV2 minus, sorry, let's see this way, U2 minus U1 plus P V2 minus V1. Now I have enough space here. Yes, that is equal to U2 plus, see, this U2 plus what? P times V2 minus U1 plus P times V1. Okay, this is the one. Okay, yes. U2 plus P times V2 minus U1 plus P times V1. To get some more space here. So this is Q. Well, all the while it's about Q. This is single equation. So what is Q now? This is the one from the above equation. What is this? H2 minus H1. That's right. Instead of writing two terms here, just a single notation H. Instead of two terms here, just a single notation H. That's why this is Q here. And if you look into this is Q here, Q is H2 minus H1. So for this system, then you have Q. So if you go to the NASA one, you can see here same. E2 minus E1 is Q minus W. Means when you have energy in and when you have work done, the balance is the change of the internal energy. Okay, and finally you have Q. Finally, see, you have H2 minus H1 is Q. H2 minus H1 is Q. Okay, H2 minus H1 is Q. And one more thing here. One more thing here. So Q is H2 minus H1. So this one, let's say initially you have a temperature T1, finally you have a temperature T2. Let me go for a new addition. Take one. Take this here. Initially you have a temperature T1, and after this V2 expansion, V2 minus V1 expansion, you have temperature T2. Okay, you have temperature T2. I will take from NASA here. See, this is like this, because here you take constant pressure, okay, constant pressure. So when you have the constant pressure, so this H2 minus H1 we can write as Cp constant pressure T2 minus T1. Okay, so another definition comes here. So Q is H2 minus H1 equals T2 minus T1. So this situation is for same P, same P. Okay, we call this constant pressure. Okay, see, constant pressure, you can see. Okay, constant pressure process. This one, eh? Yeah. So let me put this aside. So here you can see PP, same pressure. So this one is a constant pressure process. Work done. Because at the constant pressure, for a work done, you have to apply heat. Because without heat, there is no any work done. Because this heat turns into work. Okay, this is constant pressure work done process. Okay, constant pressure thermodynamic process. So this V1 changed to V2, but pressure remains. Okay, constant pressure work done. Okay, so at constant pressure process, so let's see. So Q, constant pressure process for constant pressure process. Process. Two things, three things are there. Constant P. When you have constant P, so heat addition is there. Heat addition, Q is there. Work done, W is there. Okay, all three situations. Constant P. When there is a heat addition, sure there should be some expansion. Expansion is work done. Okay, that is very important. So constant pressure process you should know now. Okay, constant pressure process. So at constant pressure process, the addition of heat, because of that expansion is there. That is one thing. But the addition of heat is equal to Cp times T2 minus T. Or we call this Cp delta T. Cp delta T. Delta means difference. Okay, Cp T2 minus T. That is one thing. That's why even in here, the NASA website, so I will do this as a new slide. See, H2 minus H1 is Cp delta T. Okay, that is Q. So now instead of Q, even without Q, you can write H2 minus H1 is Cp delta T. So I take this part in a constant pressure process. There is a change in enthalpy. H2 minus H1 is Cp delta T. So this is H2 minus H1 is Cp delta T. So let me make it some more smaller. Yes. And for unit mass, you can say H2 minus H1 by M. H2 by M, H1 by M. Here Cp by M, this is separate, times T21, T2 minus T. So Cp by M, T2 minus T. Okay, or Cp by M times delta T. Okay, yeah. Cp by M times delta T. Okay. Cp by M times delta T. This can be written as H2 minus H1 equals not big Cp, now small Cp. T2 minus T. Okay, is equal to small Cp times, if you need, you can put, yeah, small Cp T2 minus T1. It is good. And in delta terms, this is delta H. H2 minus H1 is delta H. Cp times delta. Okay, so H2 minus H1 is, here you can see it's delta big H. So that's how it is. And actually this 2, 1, P in Cp, 2, 1, and P in Cp, all should be subscripts. Okay? Now, because to me, typing all one time, it is difficult and it takes time. So now I am finalizing this. Subscripts. Okay, subscript. See, now it is very nice. So this is what NASA website also mentioned. So you have learned two terms now. H as U plus PV, and also for constant pressure process, enthalpy increase, because when the pressure is constant, of course, to have some work or something, you have to add some heat. Then there should be expansion of the gas or steam means there should be a work done. Expansion is work done. I think I have mentioned this with some rockets and all pictures in our previous classroom sessions as well. Delta H is Cp delta T. Okay, so same here. So let me take. If you see this, H2 minus H1 as CpT2 minus T1 or as delta H as Cp delta T. This should be in your mind. Okay, so this says this constant pressure process. Okay, this is one thing. So constant pressure process. Here there should be Q. Yes, there should be heat addition. Okay, Q. See Q. Q is yes. W. Okay, W means what is W? Force and displacement is yes. Okay, force and displacement is yes. So P equals constant. So small p, standard. Means no change. Of course. If the pressure maintained constant, if no heat, no work means no nothing there. So to make some active system, dynamic system for constant pressure, heat should be there, then work should be there. Okay? Can you understand? Yeah, good. And there is a name for this Cp. Cp there is a name. Cp we call what? Again, specific what? Heat capacity at what? Constant pressure. Okay, specific heat capacity at constant pressure. We call it Cp. Okay, we call it Cp. So this is specific heat capacity at constant pressure. Or you can write it as, you can bring constant pressure front.
So we can't hear.
Sorry, sorry. Yeah, SCP we can introduce. Yeah, sorry, Buddha, you should have mentioned this little earlier. Uh, I saw in chats also. Very sorry, Buddha. CV, same like CP, constant pressure, specific heat. We can have CV is for constant volume, specific heat capacity. So specific heat means per kg, okay? And here also it is like this, kilojoule per kilogram per Kelvin unit. Here, uh, later I will develop the expression for CV. But Cp, it is based on delta H, okay? Cp. And Cv, if I move one more step, for Cv, that I have to share with you how this is possible. U2 minus U1 is Cv delta T. This is very beautiful. Later I will explain you. Because today, so this is Cv. Same like Cp, here becomes Cv. So Cv is same as delta U by delta T. Delta U by delta T, that is constant volume heat capacity, okay? Constant volume heat capacity. Your unit, delta U, you know delta U unit is kilojoule per kilogram. Delta T unit is Kelvin. So CV is constant volume, specific heat capacity. The unit is kilojoule per kilogram per Kelvin. So unlike in constant pressure, you have Cp, constant volume CV. And actually, this case, later I will explain you for constant volume what's the situation. Again, for constant volume, to make the system perform, there should be some heat additions again. So this is really small cube. Yeah, that one I will explain you later. For the moment, you understand this. So starting from enthalpy, uh, we really came to know that H is U plus PV, specific heat, and for specific enthalpy, and for the enthalpy of mass, it is in times H. So H is U plus PV, and for some system, it is big U plus P, big V is big H, or E plus PV. This is from the NASA website. H is E plus PV because that is very useful term. So now you know what makes this useful because application point of view, when it's here, these are the developments. And finally, for this constant pressure work done by force due to pressure P, pressure force by moving a volume V. Yeah. So work done is PV, or PV is V2 minus V1 here. The displacement or expansion your energy balance. Q plus U1 minus W is A2. So hope you understand this. Okay, hope you understand this. And finally, through the expressions, Q becomes H2 minus H1. That's how they are. Okay, Q becomes H2 minus H1. And this is Cp delta T. So Q is Cp delta T. Okay, good. Same way, the same thing here. Cp delta T, the units are here. So H2 minus H1. Same way, U2 minus U1 is Cv delta T. So that's all Putala for today. You go through the notes and understand what Cv and Cp and enthalpy today. So you have some idea about this. So for the next class, we will go for very important, how to say, very important concepts about energy balance. Today also you learn a bit about energy balance, don't worry. So we will understand next week the steady flow energy equation and also energy balance for the closed system. Both we call first law of thermodynamics. Yeah. So our basics are ready with understanding of entropy, then about the internal energies, temperatures, pressures, volumes. We have some idea about this and two-phase systems, about the steam tables, you know about this, and make sure you do your assignment, and I believe it is submitted. So make sure that and get ready for the next session by understanding this. So next week, if we have some issues with understanding, next week we can solve this. But we both need to understand one point. Puta, lecturing on Zoom is not like, I think you can feel the difference. It's not like lecturing in the classroom. But that's why we need to have commitment from both the sides to understand and to make the class effective. So that's all. We have disturbances somehow, but we have managed to do this. So go ahead with the notes and try to understand this, Putana. If you need this note, I can email this to you after. I think I will email it to you, right? Yeah, don't worry. I will email it to you. Oh, some more. Cannot hear. Anyway, now I'm going to end the class, Putana. We will discuss whatever difficulties in the coming sessions. I know it. So bye for today. I will email the notes to you, and also you go through your notes I already passed to you. Right? Yeah. Bye, Putana. Bye.